Hi, I'm Ashay. I'm an engineer by training and a storyteller by passion. I made this podcast to talk about data science, but no math, no equations, just intuitions behind data science. The episodes are not in any particular order, and you can just tune into any episode and listen to something related to data science. Let's get started. In some of the data science problems, we want to know if two data points are similar to each other. For example, in recommendation systems, we have a method called collaborative filtering where we want to know whether users are similar to each other. Or in content based recommendation systems, we want to know if there are items similar to a particular item, so that if user likes item A, the items similar to item A could also be recommended to that user. So there is a mathematical entity in data science called cosine similarity, which we use to find the similarity between two data points. And this episode is to talk about the intuition behind cosine similarity. So first, let's understand what multidimensional data means so that we can know more about the cosine similarity for multidimensional data. So if you look at data, so data usually comes in data points with features associated with each data point. So if you think in terms of a spreadsheet for this, each row is a data point and each column is a feature of that particular data point. For example, if there are 100 customers for a particular bank, um, the names of those customers could be one feature. Then the incomes of those customers could be another feature. Credit rating for the customers could be another feature. And every single feature is a dimension. So for this, we need to understand how we visualize data in Cartesian coordinate system. So if we want to only, let's say, if we only take one feature, which is the credit ratings of customers, and if we want to plot those credit ratings on in a coordinate system, we can actually plot it on only one single axis because it's just one feature. So think of it is like a long ruler that we have, and we are basically just making markings on that ruler for the credit ratings of different customers. But if you add another feature to this data visualization uh, situation, uh, we let's say we add income and credit rating both in this situation, then you can plot the income, let's say, on x-axis, and you can plot the credit rating on y-axis, and then suddenly your data became two-dimensional, right? Because now in that two-dimensional space you can plot uh, points at which your customers lie. Now if you add another feature, like if the customers are married or not, that feature could be plotted on a third axis, or the z-axis, and then now your data has become three-dimensional. Now, obviously, you can have a fourth feature, fifth feature, sixth feature, 100th feature, and your data will become multidimensional. As human beings, we can only visualize three-dimensional data. So I'm going to restrict myself here to talk only about two dimensions or three dimensions. So, so then each data point, let's say, let's go back to that example of two dimensions where you have credit ratings on one axis and income on another axis. So in that two-dimensional space, you can identify a customer in that space with a vector which starts from the origin, which is 0 0, and ends at a particular data point with a particular income and a particular credit rating. So it's a vector, and then every customer can be plotted as a vector in that space. Similarly, in three-dimensional you will have a three-dimensional vector. Similarly, in four dimensions you have a fourth-dimensional vector, like that. So it's so in real life situations, every data point is kind of like a multi-dimensional vector. So again, going back to the two-dimensional example, you have customers which are 2D vectors in that space. Now, if you need to know whether two customers are similar to each other or two data points are similar to each other, we need to know whether the two vectors that are representing those two customers are similar to each other. Now, what makes a vector similar to another vector? So, if a particular vector lies on top of the other vector, then the you can say that those vectors are similar. So, what is the mathematical function or mathematical entity that becomes one when the uh, when the two vectors are overlapping each other? And why do I say it becomes one? Because let's say if point A is equal to point B, then A divided by B becomes 1, and the difference between A and B is 0. That's when you have A similar to B. So if you have two vectors which need to be similar to each other, if the difference between them is 0, then we need output as 1. So what, for those two vectors, what becomes 1 when the difference between them is 0? And the difference between two vectors can be calculated by the angle between those two vectors. So what becomes 1 when the angle is 0? The cosine function becomes 1 when the angle is 0, because cos of 0 is 1. So that's why it's called cosine similarity in data science, because it's the cosine of the angle between two multidimensional vectors that becomes 1 when the vectors are overlapping with each other. And I'm not saying when they are overlapping they are identical. They are similar, only the angle between the two vectors is 0 or closer to 0. So if the vectors then are perpendicular to each other, the angle between them is going to be 90, and then the cosine of the angle between the two vectors is going to be 0. And if the vectors are completely away from each other, then the angle between them is going to be 180, and the cosine of the angle between the two vectors is going to be -1. So when you have a cosine similarity of -1, the data points are not similar to each other at all. And when it approaches 1, +1, then the data points or two vectors are similar to each other. And that's the intuition behind the cosine similarity in data science. Thanks for tuning in. I made this podcast to talk about intuitions behind data science, and we'll talk about some other idea in the next episode. There will be no math, no equations, just intuitions behind data science. See you soon.